part of it.
Yeah, sure,
okay,
sure.
Cool.
So
Sorry.
this is an amplifier. I'll just restart again.
Right.
So we are solving the problem of pre-layout designing. And we start with a schematic. The designer gives us a schematic and some specifications associated with it. Like let's say this is an amplifier, so gain has to be higher than this value. The unity gain bandwidth must be greater than this, and all of those specifications. But at the same time, make sure that the objective function is also kind of minimized or maximized, depending upon what the objective is. So how do you solve this problem? So we have divided this whole thing into 3 stages. First is called as graph of circuits. Second is the graph surrogate model. Third is the constraint optimization. Now let me just go through the whole pseudocode of it. So first step is learning a graph. Second is doing a label propagation on the unlabeled instances. Third is generating a surrogate model. And fourth is the constraint optimization. Let's go on to the first step. So the general literature around this particular work has been is that when you have this particular schematic, consider this whole thing as a graph. So what you do is make multiple such graphs. So it becomes a graph regression problem. The label will be gain, UGB, gain margin, phase margin, corresponding to each of the circuit instances.
I have a question about the creation of the graph.
Yes.
What are the nodes and what are the edges?
According to the literature, each node is going to be the circuit component, resistance, capacitance, transistors, all of those things. But as I mentioned, you have to generate multiple such graphs, and it is always going to be a supervised setting problem. So obviously, it is going to be computationally very expensive. Generating those labels is also going to be very cumbersome task, right? So what we are saying is reformulate this whole thing into a node regression problem and a semi-supervised learning framework. How do you do that? Instead of taking this whole thing as one graph, consider this thing as a whole feature vector, right? So these are multiple such feature vectors, and generate labels only corresponding to few samples, keep most of them as unlabeled. Now, how do you generate a graph out of it? This GVEW, that is a representation of a graph. This W corresponds to the weighted adjacency. How do you get that? By solving this optimization formulation. It has 3 steps. First is called as the directionless energy. So what it says is the circuit instances where the difference between the features is pretty less, make sure that they are connected with very high weights, right? So that is the first term. Second is the sparsity term. You don't want the graph to be very dense or fully connected. So you are incorporating a sparsity term. And the third one is the regularizer, just to make sure that your weights does not go down to 0. So from here, you end up with a graph where you have some samples which are labeled. Most of them are going to be unlabeled. Second part. So this completes our first task. Yes.
What's the node here?
Node is going to be a whole circuit.
Oh, a whole circuit.
Yes.
Okay.
This will have these feature vectors like maybe all the design parameters like VDD, the width of your transistor, length of the transistor, all of those things that will contribute to the one feature vector of a node.
And then the X's are what exactly?
Feature vectors, that is the design matrix. So as I mentioned, like let's say this is a circuit which you have in hand.
Yeah.
So the VDD, so it can go to 1, 2, 1.5, 2.5. All these real values are going to be VDD. So these will contribute to different instances. Similarly, for W1, it will be maybe 100 micrometers or 200 micrometers, something like that. So that will be another row. So something like that. So
It's the stack of all the bits.
Yes.
But so the I and the J are going to be different instantiations of the
so this
circuit.
is Xi and Xj. So in that way. So it is going to be ON square times. So because each one will be computing with all the different features available within that particular stack.
Yeah.
Right. Now, why do you need a surrogate model? So the problem with generating labels here is, now let's say you take a feature vector. This feature vector is your one circuit. You pass it through a simulator. As the circuit size increases, the chances of generating one particular label may go up to, it take time up to maybe 30 minutes or more than that. As the circuit size increases, it can go up to hours. So you can understand, if I just want to generate a label data set for 1000,
like some voltages.
gain, UGB, gain margin. So all of these are labels. So it's a multi-label scenario. So generating just a label data set of 1000 samples will take maybe weeks, right? So we don't want to do that. So we have to come up with a way which kind of approximates the working of a SPICE simulator. And that is done by this graph surrogate model. So now what you do is, you take this graph with few labeled and most of them unlabeled, pass it through a GNN. GNN will train only on the labeled sample sets and do the label prediction corresponding to the unlabeled ones. So this is how you come up to the third step, second and third. This YU is the label prediction, so which you can see over here. And once you have done that, you have a GCX GNN, which is your graph surrogate model, which is going to serve the purpose of your SPICE simulator. Now, the fourth and the final step. Take this surrogate model, incorporate it with some constraint optimization formulation like EASCO and ASTROC, and get the most optimal design parameters. So here, for constraint optimization, we are proposing two algorithms. First is the EASCO, which is also called as the static optimization framework, and second is the ASTROC, which is the dynamic learning framework. So let me first explain what is EASCO. So you can see this one. This is the stack, which is the first step here, right? Generate a graph by using that particular formulation. Next, train a GNN on it, get labels corresponding to all the samples. This is the step. Now, let's say originally your graph was 1000 nodes. Now you observe that out of the 1000 nodes, there are just 20 nodes which are satisfying all those constraints. But can you say that they are going to be the most optimal ones? No, right? So what you do is take these 20 nodes and compute the bounds on the features of those particular nodes. Pass it to the D algorithm. That D algorithm will minimize your objective function and give you one or maybe some multiple solutions based on the convexity of your objective function, right? But now these particular new solutions which you have will not have the labels. So so it again becomes this particular problem. So what you do, you learn a graph and do the label prediction, and you will most assured get these solutions that these optimal design parameters will have the labels which have satisfied all those constraints, and as well as the objective function is minimized. But what is the problem? Why do we not stop at this particular place? The reason is, as the specification size increases, we have observed that the chances of getting those particular nodes might end up to 0, right? So initially I mentioned that there might be 20 nodes, but what if the number goes down to 0, right? So in that case, we need some other alternative, and that is the dynamic learning framework. So what we do here is, we start with all the label samples, but very few label samples, just 20 or 50, right? You re-rank those samples based on what criteria? Based on the criteria of the probability of the satisfying constraints, the samples which does that should be placed at the highest of the stack, right? So take just few samples out of it. Now, pass it through the D algorithm, get new feature vectors, but you don't have the label for it. It again becomes this particular problem. Get the labels using the GNN. So now you have this particular problem where the stack is completely labeled of maybe just 50 samples. Again, re-rank it. Again, pass it to the D algorithm. Keep doing it until you have started from a space which was uniformly sampled across the D-dimensional space, but now you're converging towards a space which will most probably give you the most optimal design parameters. Put an iteration budget, or maybe make sure that the difference between the loss functions or the objective function is whatever that can be the iteration budget for it, and at the end of it, you're going to get the design parameters which have satisfied all the specifications, and at the same time your objective function is also minimized. This is the whole work.
Very cool.
Yeah, thank you.
So may I just try to say this again, like based on my understanding?
Yeah.
So you may have certain, let's say, a certain number of circuit instances.
Yes.
And you don't know whether it satisfies this problem or
Correct.
not. But you can construct some features, right? Like some design parameters, and use these design parameters to solve this problem, to connect all of the circuit instances into a big graph. Kind of each node corresponds to one circuit instance.
Correct.
Right? And you also have the node features correspond to these features, and also node labels. Only a very few number of circuit has the labels here.
Correct.
And then you use GNN as a kind of semi-supervised learning way to train on those labels.
Right.
Okay. And then you also get some labels for maybe those other
Unlabeled ones. Yes.
Okay.
Yes. Correct.
And then I lost the rest of the thing. Yeah. So I keep this point.
The question is, do you just assume you have some labeled ones, or are you also, depending on the graph, deciding which ones are the most optimal to label?
No. The labeling is done in a random way, because obviously we don't know where the optimal solution will lie.
But can you do the graph without the labels?
Yeah.
So
the
but
graph
then
is just
technically you could decide, okay, a very central node is the one that I should get my label for.
maybe
Or do
that
you?
can be another
Yeah.
approach.
The
of
question
doing
is,
it.
can we optimally decide which labels we should have so that the information is maximized?
Exactly,
Correct,
right?
correct.
Okay,
Yes.
but you just assume you have some kind of random labels available. Okay, and then you go on and you have two different methods, but
Yes.
in one essentially you say, let's train a re-ranker on
Correct.
these things,
Correct.
and whenever we run out of labeled samples, we just kind of make some more and use the GNN to
Right.
label those,
Correct.
and then we
Correct.
re-rank again.
Right. Right.
And so we try to go up.
Correct. Correct.
Okay.
So
Yeah.
I have a question here. So here you will have some labels,
Mhm.
some label Y for, let's say, those unlabeled nodes.
Correct. Correct.
And then I lost the rest of the thing, like how.
So,
Yeah.
Yes. Okay. So the thing which you're saying, we have reached here, correct?
Mm-hmm.
So now what I was saying is, let's say you had a graph of 1,000 nodes,
Mm-hmm.
okay? Now you generate, now you observe that there are only 20 nodes which are satisfying all your constraints.
So here I have a question. So
Yeah.
So for all the constraints here, each one of it could be correspond to one label here, right? So
Yes.
one type of label.
Yes.
Okay, you are doing something like a regression task, kind of,
Yes.
and this could be multi-dimensional regression.
Right.
Okay,
Right.
I see. Okay,
Right.
and maybe a part of them satisfy this, and then you will throw them into the simulator to gather the ground truth result. Is this?
No.
No.
Because again,
Yeah.
even if they are 20, they are still much, right?
Mhm.
You don't want that time to be wasted as well.
Mhm.
So take those 20, put an input bound on those on the feature side, right? And run a D algorithm on it. So what the D algorithm is going to do is, it is going to minimize your objective function, or let's say a generic term should be optimize your objective function, right? And generate one or many new solutions based on the convexity of your objective function.
Mhm.
But those solutions will not have labels, correct? How do you get the labels? So this problem again becomes something like this, where you have some labels, most of them unlabeled. So, but you have already trained your GNN. So that graph surrogate model will be used to put the labels corresponding to those new solutions.
So can you see how you get this new solution? Like a kind of here solution, I guess you mean a design of a type of
Yes,
design.
the labels like the gain, UGB, those are my solutions.
So basically, GNN output will be a bunch of like labels, or you call it
Yes,
solutions.
yes.
Suppose 20 of them satisfy the hard constraint there,
Right.
and then you are saying you want to run some like a D algorithms, right?
Right.
What is D
A
algorithm?
differential evolution algorithm. So
Okay.
that's a evolutionary algorithm. That's a heuristic one, right?
Oh, okay.
So because you don't know the form of your objective function, right? So you cannot decide on previously that whether it is going to be convex or not. So all your KKT conditions and all of those things, they may or may not work there,
Mhm.
right? So you want to have a heuristic algorithm which will satisfy
So
that.
that is much faster than the simulator.
Yes,
kind of, like
yes,
but a
yes.
heuristic or traditional heuristic
Correct,
algorithm, right?
Correct.
Okay, run on those, and then you will select the best one.
Then you will get the new ones, correct? That solution will
Why?
be one.
Why this is a new one? Yeah.
See,
So here,
Huh.
where I have 20
correct?
different circuit instances,
Yes,
right?
correct.
And the GNN output tells us they satisfy this hard constraint,
Correct.
right?
Right.
And then you will use a heuristic, which
Mhm.
I know is much faster, but maybe slower than GNN, but faster than simulator.
Mhm.
Run on those, maybe get some like some objective or some objective value for this circuit.
Right.
And then why you say there's a new design or new system?
Because those samples were not previously available within my graph, right? Because I have what I have,
Then how you GNN can infer over them?
see, the thing is, because we have used different algorithms like GAT and SAGE, right? So
Mhm.
these are inductive in nature. So even though these samples were not previously available in my sample, once I freeze my model and do a label prediction corresponding to a new graph, it is most likely going to give you the right solutions. Because I understand when you're saying that how can we get those solutions, that is going.
So
Yeah.
my understanding is so you actually have a series of graph circuits, like
Right.
your series of circuits,
Correct.
and all of them are like previously already designed, and each of them correspond to a node in the graph,
Correct.
right? So and you select 20 of the nodes,
Right.
right? Although you don't know the ground truth, but you have the heuristic to run to collect some information.
Yeah,
for
but the
this.
heuristic is not going to generate the labels. It will generate the new features.
What kind of new feature?
See, the thing is, now let's say you have the stack, right? Okay, these 20 nodes corresponding to that, you have the labels as well, correct?
Mhm,
Because we have done it a label prediction. Now, let's say these are the nodes which are satisfying all your constraints,
Mhm.
right? Just focus on this particular area, the feature one. Okay?
Okay.
Take the bounds on it. Understand where the feature vector is moving, right?
Okay.
Right? Within that particular bound, run a D algorithm.
Oh, so the D algorithm is not try to infer the label of this 20, but more like you kind of its input is some parameter space.
Exactly.
Okay, and GNN is trying to give you a more sharper parameter space, and then you put that into the curious. Okay, I see. I see the point.
And then you
And-
get the new labels
Yes.
Yeah.
for
yes,
the ones.
yes, yes.
Okay, I
Very
get
cool.
the idea.
Hi.
Thank you.
Thank you very much.